Okay, if what we're talking about is data analytics, why are we talking about probability and statistics, right? So let's talk about the data. Okay. First of all, basically, we're in the world, quote unquote, before big data. All right. So if you think about big data as being everything, you know, all the attributes we talked about last time. If you talk about just data itself, let's assume it's manageable in a file, so you don't need this Spark server or whatnot. Okay. Then what distinguishes big data is the variety. The fact that you have audio data, you have text, you have all kind of stuff, right? Well, a smaller subset of that is the structured data. Okay, that's tabular data, data that comes in table. Now, an even smaller subset of that is when you deal exclusively with numerical data. Okay, so if you think about it, what we're covering today is a restriction, but it's also not a limitation. What I mean is this: it's restriction in the Venn diagram sense. That you're not talking about audio data, you're not talking about qualitative data like male or female index, but you're talking about something that's numerical. So it's a restriction. But it's not a limitation per se, because most of the data you deal with will be numerical. Okay, and statistics has been around for the longest time. And as I told you, you shouldn't try to be building a machine learning model as your first instinct. If your problem satisfies the constraints that allows you to apply classical statistical method, you'd be really stupid to immediately jump to machine learning based algorithm, right? Because statistics is based on hundreds of years of mathematical formulation. All the proof are precise, so you know exactly what you're getting. With machine learning, there's always a little bit of experimentation, hit and miss. But if in terms of statistics, if you prove your convergence, you prove that this is the quality, this is the essence of how your data is generated. It's generated by this random process and so forth. This is how the data is gathered. You are guaranteed to have the right conclusion. Okay. So in other words, yes, smaller in the sense that you can apply to numerical data, but big in the sense of application. Much of what you have in real life will be already numerical, and you'd be stupid not to use statistics when you can. Now, in terms of analytics, however, let's talk about the limitation again. The limitation here has to do with the fact that it's mostly about distribution. Okay, how they move this thing? Can't move this. For some reason, once I share the screen, I can't move to the right. Well, oh, it's on that. That's you're right. Nope. Never mind. Okay, I'm not going to spend too much time on this. Basically, you are studying most of the time about where things are, where our data distributed. You know, what's the value of X? What's the average value? Where's extreme N? Where's the minimum? Where's maximum? So you're basically studying X. Occasionally, you will study about relationship between X and Y. That's when you bring in things like regression, you know, occasionally. But this is where machine learning becomes a lot stronger. And sometimes it's also about regression, but not regression across variable, like from X to Y, but across time, from X today to X tomorrow. Okay? So, again, it's huge. This area is huge. What I'm talking about today is 3 hours, yes, but in fact, it covers a whole scientific discipline. You get many PhDs doing statistical analysis, right? But from our perspective, you only come here. Well, you come here because you know that your data are numerical in nature. You come here because most of the time you're interested in the actual values of X itself. You know, where are they? What's your attributes? That's the meat of your your analysis and your application. You're not so much trying to map from X to Y, okay? And you're not so much trying to map from X today to X tomorrow. You do that, you can do that, but I would maintain that the second and the third part that we're talking, that I just mentioned, are more and more becoming better and better handled with better results from machine learning. Okay, so basically, if you talk about numerical data and about distribution, that's where we are. Now, traditionally, and a lot of what I'm doing is quite traditional. In fact, I've been teaching like probability statistics course since I was a little bit older than you. Just come out, well, maybe a bit older than you, because I started tutoring when I was a master's student, or actually my senior year, I think. And that was mostly like, calculus and statistics and whatnot, I think. So eventually, what I'm trying to get at is that the curriculum that I'm going to follow through here today is fairly traditional. What's not traditional is the fact that I'm going to give you guys an emphasis on how it's the implication on the sort of like the data science part of it. And the other thing is, as I mentioned in the line group, that I won't have time to cover everything. So when I come across the topics that you guys already covered in the first year, I expect you to raise your hand and say, I know this really well, or something like that, okay? Or I don't know this really well, but the class does know this very well, okay? That's because we need to save time. Now, the loop goes like this. You start with descriptive statistics, right? That's sort of like a continuation of what we did last week, except last week we were talking about visualizing everything. Now we're just visualizing numerical data, okay? And once again, we're dealing with data distribution, just the X value itself. So you deal mostly with things like histogram, where are X distributed. Insofar as you're trying to relate X and Y, maybe you deal with things like scatter plot, okay? So you're visualizing, you basically, okay. So you're visualizing the data, right? Now, when you're visualizing data, well, I just hit everything, but basically, the same message applies as last week, which is that you visualize the data because you're a data scientist. You want the data to tell you how to form the hypothesis, okay? When you visualize the data, it looks like it has distribution that's bimodal. So you form a hypothesis that it is a bimodal distribution, okay? So it's an input to your data science pipeline, the data science process, okay? Now, on the other hand, there's a lot of projects out there where visualization is the end of the game. In other words, once you get the visualization, you get the right insight, you can actually make a strategic business decision because you identify some features just from looking at the data. And that's the end of your maybe analytical work, okay? So the rest becomes a matter of business, turning your insight into action, right? Okay. So basically, like I said, it's about characterizing distribution, and this is where, I don't know why I can't. Yeah, I just accept. I can accept. I can't move the damn screen for some reason. Not Well, if you look, this is something I would expect you should raise your hand at this point. Last year, I already covered this. Things like central tendency or dispersion. Have you done that? Mean, variance, standard deviation. If you haven't, then I would be very sad, or not sad, but alarmed, because we're going to spend a lot more time than we need on the subject. Well, basically, like I mentioned to you, มันเลื่อนไอ้นี่คอมเมนต์อะไรพอเริ่มแชร์สกรีนแล้วมันเลยไม่ได้หรือว่ามันต้องเอาเนี่ยไม่ใช่ให้มันโฟกัส Anyway, he's dealing with that, right? Okay, I mentioned last time, right, that if you were trying to make shirts for a bunch of people, okay, a different population than you used to, right, and you limit it to a communication, you can't. I don't know if I gave you this analogy already, the tailor. No? Okay. Well, imagine that you are trying to make shirts, right, to sell, or you're trying to you own a factory, right? And you're in the market and you're trying to calibrate the size of your shirt. What's medium, what's small, what's large, right? So the idea is to give a general measurement of the body size, okay? So once again, data is about individual records, okay? What's your size, what's your height, what's your width? But statistics is not about one individual. It's about pooling everything into a population information. So the first natural thing that comes to mind is what? An average, right? Right? What's an average? Height, what's average? Width? Okay, that's called measure of central tendency. Now, I'm not going to talk, I'm not going to say anything except for the fact that there are basically 3 ways of measuring central tendency. If I line up all your heights, add them all up, and divide by the number of people, that's arithmetic average, okay? There's also a geometric average. That's multiply all your heights together and take the nth root. So if I have 3 people, I have 3 people multiply the height and take the cube root. But in practice, that's rarely done. So it's not geometric average that you're talking about. Geometric average comes in if you are into finance, okay? Then come talk to me about that if that's your project, geometric average. But for most of the time, when I say average, I mean arithmetic average, okay? In statistics, usually that means means, okay? It's a different one. I won't go to distinction as to what the difference between mean and average, but you can say there's some conceptual difference there. But anyway, I take up all your height, divide by the number of people, that's the mean, right? If I measure your height to the nearest centimeters, and I say, what's the most common height? Say 168. That would be the mode, the most common, okay? So if I do the histogram of the height, it's the one with the sharpest. Now the mode's a little bit tricky because nobody has exact same height. So I have to do, you know, same height up to the nearest centimeter or something like that. Now what's median? Median is when I line you up from tallest to shortest and I take the middle guy. If there are even number of you, I take the middle 2 people and do arithmetic average. That's it, okay? So that gives you an idea of where the middle ground is, where everybody clusters around. That's an average, that's most intuitive. So if you only have one value to record, that's the value you record, right? If you can record a second number, what would be the number you use? Okay. This is where I can write. Okay. เดี๋ยวนัดทำให้พี่วาดรูป Right. If you can record a second value, you can imagine that, you know, you're selling one shirt, one size fits all. That would work if you are talking about people of the same kind of average height. If you're talking about people, a group of people where you have very short, very tall, right? Or very thin, very fat, and so forth, then there's a lot more dispersion, okay? There's a lot more dispersion. Then you would have to say, well, around this mean of 165 centimeter, sort of like plus minus, how wide the range, okay? How wide the range? That's a central dispersion. Okay, and the dispersion number you have, the basic ones are standard deviation. You know that or not? Please tell me you have heard of that. Yes, yes. Okay, standard deviation. Okay, you know about mean absolute deviation? Well, mean absolute deviation is the common sense measure. The reason you work with standard deviation is a little bit historical. Has to do with the mathematical and computational limitation, as it were. It's easier to do things like take the square and square root than it is to say if then. Okay, if I want to say deviation from mean, if you're taller than 168, you're 171, that's 3, right? But if you're 165, that's also 3. So when I implement this on a computer, very old computer, I have to say if less than equal to 0, multiply by -1 and record the number. Okay, so that's very, I guess that's very time consuming, let's say. But it's easier to take the difference and square it. Okay, so -3 square becomes 9. Okay, the problem is once you average it, the unit of measurement is square, so you have to take the square again. square root, sorry. Okay, so that's why you work with variance as opposed to mean absolute deviation. And once you get the variance, you divide, you take the square root to get the standard deviation. Now that's an anecdotal. It's not really the true story. A true story is more probably having to do with parameterization of normal distribution, but we'll come to that. Well, what's another thing of measuring the dispersion? It's the range, right? Minimum and maximum. Or I can line you all up, and I can take the difference in height between the one who is 1/4 of the way tallest and 1/4 of the way shortest. Or I can actually do it from the top 10% and bottom 10% and so forth. Right. Now that's what we mean by measure of so if I want to know where the heights are, there, this is where you are, right? If I want to know how much, like this, that's the dispersion. เอาเป็นขาวเลยก็ได้แล้วสลับเอาง่ายกว่าไหม Okay, never mind. Right. What else? What else can I measure? If I have the luxury of two numbers, right? I measure the mean, say standard deviation, my second number, right? So you have two numbers, right? You allow one more number to register. Well, that would be how skewed the distribution is. This is kind of symmetric. You know, there's a lot of people taller than 168 and shorter than 168, and so like falls off evenly, right? Or is it something like something like this, right? Chances are it has to be something like this, because if it's symmetrically falling off, then you have negative height pretty soon, say. Okay, so this is a skewness. Skewness. It skews to the right, it skews to the left. All right. Now, you intuitively you know what skewness means, but what does it mean in terms of measurement? How would you detect it? Right? Well, statistically, if you take an average, okay, if you take an average, that means your height divided by the number of people, you get the mean. Okay? If you take the height difference, square. Take the average, that's the standard deviation. If you take the difference and you raise it to the power 3, okay, that gives you the skewness. So you can spot the trend, right? It's you can imagine that this, you can keep going and say, well, if I have the luxury of 4 number, what would I record? I would record the average of difference to the power 4. What would that give you? Well, that gives you something called kurtosis, and it doesn't mean anything to you right now, but I'll come back to it. It's basically how widespread. So this distinguished from this versus this. But how do you distinguish this versus this? Okay, it's not just parameterization. It's not just spreading the standard deviation, but it's actually the shape. You know, the shape. Sorry, let me do it something like this. Oops. Apple ID. Apple ID. Not now. Okay. Between this, oops. Okay. พอไม่ใส่ Apple ID มันเลยเขียนไม่ได้มั้งนี่ไง Okay. Between this and this, you can see there's something qualitatively different about the distribution, right? It's very narrowly focused and widely focused. Well, the short answer is there is a very classical distribution that looks like that. Okay, and that happens to have kurtosis number of 3. So you would call it sort of like a baseline. If something that's more widespread, you say it has excess kurtosis. All right. If it's less than 3, then you say it's leptokurtosis. Lepto means smaller. Hyper means more. Right? Hyperthyroid. Okay. This is leptokurtotic. So if this is the nice shape, something like this would be leptokurtotic. Right? Kurtosis too small. Anyway, so those are the. Remember, I told you guys that you're visualizing the data, right? Nowadays, you have Excel. Well, 20 years ago, you have Excel that can do histogram. You also had a fax machine back then, so you can fax you can fax the histogram to your factory to make the shirt. And the shirt say, okay, if this is a histogram of the population, you can cover 25% with this small, and maybe for medium, you can cover like 68%, and the 90% of them you can cover with small, medium, and large, something like that, right? Well, you can't send the picture. You don't have a fax machine. You only have a telegram. Go back 100 years. So what do you send in the telegram? If you can send one word, you send the mean. If you can send 2 words, you send the standard deviation. If you can send 3 words, you send the skewness, right? If you can send 4 words, you send the kurtosis. Okay? You didn't have a fax machine. Okay? And that's how you describe the data. That's how you visualize data. That's how you analyze the data. And before you have mathematical model, before you have machine learning, visualization is analysis. That's the short end of it. Okay? So nowadays you have fancier way of doing visualization. You can do a little bit more insight. You can draw more narrative. You actually can't draw that much more insight, but you can draw better narratives. And that's what we were talking about last class about infographics, right? You basically representing things like average or growth or difference and so forth, but you're doing it in a way that gives you a narrative, a flavor to it, right? So now let's clear all this and go back to, right, admin. Okay, so once you do that, and that's basically just one lecture, right? Probability statistics, imagine it's a 15 class lecture, right? So that's just one class, basically, right? And the second class then would deal with building probability model, okay? And this would occupy maybe another 40% of the class, of the semester. And then statistical inference would maybe cover the remaining 50% or 60% of the semester. Now, what's the difference? You can think of it this way. A histogram, okay, think of visualization in terms of histogram. That's the easiest way of thinking. Histogram is real life. It's how data is distributed in real life. You want to model it, okay? So if you think about it, it's like putting a function to that distribution. But before you build the function to that distribution, you have to sort of like build your way up. How do you talk about probability? What does it mean to have probability of 80%? Okay, what does it mean to say that there's a probability of finding someone who is between 160 and 168 centimeters tall, something like that? So you have to build up the probability models. But once you build them up, you have functions with parameters. But the parameters, then you leave it as degree of freedom, as something that you haven't specified. So you build up a whole bunch of functions. Each function has its own parameter set, and then you leave it there. You call that probability models. So you put that in your bag, and you take that to your work site. And you go to your work site, and you look at the data. And the data looks like it is from this probability family. It looks like that. So you whip out this probability model that you think is the right one. Then you stretch the shape of the curve to fit the data. And that's called parametric estimation, right? So once again, the first step, you look at the data, it has some kind of distribution. The second part, you build up a whole bunch of probability distribution. One that looks very symmetric, one that looks skewed, one that looks very skewed, one that looks very symmetric but very, wide open, one that looks very narrowly focused. You build a whole bunch of them, okay? And you take that into your toolkit, into your bag, into your work bag, and you go to your work site, and you look at the data and say, this one looks like this. Let me take this one out. Once you take this one out, it has 3 parameters, right? You stretch the shape of the curve to fit the data, and that's just statistical analysis. Okay, so that's the thinking. That's the thinking, and in fact, that's how we'll proceed. So the probability models. Now, the probability models. Can you see? It's about constructing from the ground up. Now, the concept here, okay. I'll spend 5 minutes on this, maybe less. What do you mean by probability? Okay. In fact, the earliest definition of probability has nothing to do with this kind of chance happening. It's about your belief. You know, in fact, if you look at the etymology of the word probability, it means truth. In other words, is he a good guy? Probably. That means, yeah, I kind of believe he's a good guy, right? Right? So it's not about occurrence of items of events. It's the likeliness of the truth of this proposition. Okay, let's turn that to different. Instead of, is he a good guy? Well, likely, to something else. Is it going to rain tomorrow? Once you turn it to, is it going to rain tomorrow? It's also a statement of belief. Let's say you give it like 80%. But then you can start thinking about, wait a minute, we're living in a seasonal Earth. So in August, same time this year, okay, from historically, this period of the month, okay, with this lunar cycle, 8 out of 10 days in the past, you had rain, you know. So you say something like, well, probability of raining this week is 80%. Now you start to have things like events, like counting the average, using the average to protect the average, right? So that would be like the frequentist. So you can build up the intuitive. Now, if you actually go to a proper, say, graduate level probability, and I look, huh? Okay, last time, okay? Control your bowel movement. I mean, you big boys now. Okay? There's some actually adult nappies you can buy if you can't. Okay? But do control your bowel movement. Good. Right. If you start with a graduate school, probability and statistics, you would actually start by counting cards. Like how many cards are there? There are 55 cards. What's the probability of red? That's 26 out of 52, right? What's the probability of queen? That's 4 out of, okay? So this, when you did this, you did 2 mathematical operations. 2 mathematical steps. 1, you assume all the cards have the same 1 over 52 probability. That's your assumption. That's your basic atomistic probability. Then you define your event as red. You define your event as queen. And that event becomes a collection, right, of individual smaller events. So the basic event is individual card. Okay, and there are 52 events. Of those, 4 basic events count as composite event you call queen. Of those, 26 count as composite event you call red. This is how you build up, right? And then you can have what's called axiom from this combinatorics. You notice that let's make a convention. You only need to make one convention. That the probability of certainty is 1. Means anything that happens anything has to happen. You draw a card, you get a card. That's probability of 1. If you don't draw a card, you don't get a card. And if you don't put a joker card in the deck, what's the probability of getting a joker? 0. So basically you have 0 to 1. And probability of any event is non-negative. You can't have negative probability. Okay, so there you have probability starts at 0, highest is 1, nothing negative, something in between 0, between 1, and if 2 things are independent, probability adds. And that's axiomatic. Okay, by which when you say you add probability, that means you multiply them. It sounds a bit silly, but anyway. what's the probability that let's say there are 20 boys and 20 girls, okay, half and half. There are 10 shirt wearers, and there are 90 no, that's not good. How about glasses? Okay, glasses is good. 30% versus 70%. Okay, and this is important. Boys and girls become nearsighted at the same rate. Okay, if it's not the same rate, then chances are I will pick somebody who's wearing glasses. I know it's a girl because girls wear glasses more. But no, not this case. Okay, you have a 30% glass wearer and 50% boys. What's the probability that I'll pick someone at random and I'll get a boy who wears glasses? It'll be 0.5 times 0.3. Okay, probability multiplies like that. Okay, and there's something called measure theoretic, and this is something that's heavy duty mathematical. It's a lot of fun, but I think it's not for you. Okay, it's not for you. It's for you if eventually you find yourself interested in starting career as a financial engineer. Then it becomes fairly critical. Okay, measure theory. Anybody imagine themselves going to become financial engineers at some point? No? Okay, all right, not for you then. Good. But what's good about this is there's a fun fact here. We're gonna learn about things called random variable. And if you know measure theory, you know that it's actually very false. It's not random and it's not a variable. But okay. So the mathematical construct that you're going to have to learn today, basically there are roughly three kind of things. Okay. One is the notion of random variable. Okay. One is the three kind of functions you're going to deal with: probability mass function, probability density function, and cumulative distribution function, and the notion of expected value. Okay, that's all the mathematical construct that you will need. It will come to this form when you build probability model. And then the rest of your time will be spent building up catalogs, like I told you, of distribution. Now, the first classification is between univariate and multivariate. Okay, remember I told you sometimes you deal with X, sometimes you deal with X and Y. Well, this is a little bit like that, but it's not. It's not knowledge of X gives you knowledge of Y. It's a distribution of X and Y together. Okay, so it's a joint distribution of two random variables. In fact, you don't have to have two. So most of the time, I'll still call them X, except it's a vector now. It's X1, X2, X3, X4, X5, X6 are jointly distributed. Okay. Now, why would you study them? Because X1 and X2 are not independent. If they were independent, you can do the arithmetic I mentioned earlier, right? You have a distribution on boyness, girlness, and you have distribution on glass wearing. And if you need any kind of joint information, you multiply them. The whole point of having multivariate distribution analysis of X1 and X2 or X1 and Y and Z is because they are not independently distributed. You can't just multiply them at the end. Okay, it make life too easy. So basically, you have multivariate and univariate distribution. Think of them as univariate as one histogram that has one axis. Multivariate has 2 or 10 or 50. You can have as many as you like, except you can't plot them. You can only plot 2, right? So multivariate, univariate. Now, multivariate, you're going to learn maybe 1 or 2. Well, actually, you're going to learn 1 because this one is not really for you. But let's say normal, multivariate, normal. Univariate, however, you learn a lot of them. You learn about discrete and continuous. And discrete, the main ones are here. And continuous, the main ones are here. Okay, so we'll go over them. Don't worry. Okay, you have to. Once you learn that, then you go to the loop of this guy, of statistical inference, right? And this is what I meant earlier by having built up a collection of probability models in your tool bag. You take them to your work site and you take out the data and you try to match it. Ah, this one looks like this, and you take it out. And then you fit the parameter. That's called parametric estimation. Okay? That's a big part of what you do. In fact, I would say this step is the joint step. It's a step that is common to all the machine learning work. So basically this comparable step, it's a little bit like heating. You know, whatever, you're making souffle, you're making omelet, you're making pie, and there is a central process where you heat something that you turn it from raw to cook, something like that. Okay, so this is that essential step. Everything else builds up to this, and everything is a consequence of this. Okay, this is the crux of everything. Okay, once you make the parametric estimation, then you can do certain things. You can do the opposite. You can say that somebody already built this, the estimation, and he claims that the average height of students is 168. Then you can test hypothesis if whether or not this is true, or based on the data, it shouldn't be true. Okay? Now, hypothesis testing seems like nitpicking, but actually this is how the scientific process proceeds. Okay? So you can't really do things by parametric estimation. Parametric estimation, you can say, is scientific, but the way science works is not from estimation, it's from hypothesis testing. For example, I claim that smoking and cancer is not related. Okay? The scientific process is not to estimate correlation between smoking and cancer. The scientific process is to say the null hypothesis is smoking does not cause cancer. I have to reject this in favor of the alternative hypothesis that smoking does cause cancer. All right? That's when it becomes something usable. It's more rigorous. It's more rigorous. So you see here two words, parametric estimation, and actually the word parametric I shouldn't put there. I should put something like statistical hypothesis testing, or just hypothesis testing. Okay, you can just say hypothesis testing. It's like a proof. It's kind of proof, right? It's kind of proof based on the data, and it's a rigorous proof, and it will be used everywhere. In fact, something along this line is also a key part of data science. So when I say everything leads up to parametric estimation, you can say that you don't exactly come down. Parametric estimation and hypothesis testing really are the top of everything, the key process of everything. In statistics, in data science, they'll have slightly different flavor to it, and they won't call it hypothesis testing. Okay, it'd be something like machine learning and model validation. You have different terms, and the way it's done is slightly different. Okay, but it's those achieving those things. It's getting to the insight, quantitative insight, and verifying that this, yes, is the truth that you are willing to bet your life on. Okay. There's this thing called model search, but I'm not going to talk too much about that. I'll show you how it's done in Mathematica, very easy. It's basically find the best model. It's saying that instead of you looking at the data and whipping out the probability model, you actually ask the computer to, please, you know what I want to do, just go through them. Okay? So this is more akin to modern data science than probability traditional statistics. Why? Well, because if you're a good statistician, you don't need computers to tell you, because you can actually, you know, it's like a doctor based on certain measurement of your blood or of your liver value or something like that. He's got a good diagnostic, right? He doesn't go to computer and say, give me a list of 5 possible diseases, because I don't know what I'm talking about. You don't do that. So self-respecting statisticians don't do that either. So that's why historically this is not a major thing. But with data science and machine learning, the model space is so huge, and the whole point is that you don't know which model you can apply. So it becomes a normal thing. becomes a normal thing to ask the computer to, please tell me which one you think works best. And I'll verify from there on. Okay. Now, finally, goodness of fit. Well, this is a little, goodness of fit is like overall the quality of your model. This is also like a model validation. In fact, I would say that you see 1, 2, 3, 4, right? Parametric estimation and model search are kind of similar thing, except at different level. Parametric estimation means you have the F, you don't have the parameter. You're trying to find the parameter, okay? But if you take a step back, you don't even know what F is, then it's model search, right? In fact, there's no technical model for model search, because once again, statisticians don't really do that. But when you step back, you don't know which F to do, you search over F. With hypothesis testing, I claim that the parameter is theta. Theta is zero causation between smoking and lung cancer. Alternative is it's positive. Okay? So that deals with checking the truthness of the parameter. Well, goodness of fit also checks the goodness, but not just the parameter, but the overall fit. So it does the same thing, but for the whole F. I don't care what parameter you have. Okay? You just come up with your model. And your model is a parameterized F, meaning F with a function, and I tell you, does it look good? Okay? So you can imagine that these are all the top of the hill. Okay? And everything falls from there. Okay? How you use it. And again, how does it apply to ML? Just to give it a little bit heads up. Well, you do this when you don't have the need for ML. Okay, when the data has satisfied certain thing, you have a standard disease, you treat it with standard medicine. It also validates ML. You know, this hypothesis testing, you can also do goodness of fit for your model. It doesn't have to be statistical model. It could be neural network model. You can do goodness of fit there as well. And it supplements, obviously, that's sort of like a truism. You can always supplement one technique with another. Okay, so there. Now let's get to the meat of this. By the way, who hasn't? Oh, you need bowel movement. Okay. Any of you have gone through the Australian Bureau of Statistics website that I gave you? No? Go through that. When I give you guys something, it's a hint. Okay? It's a hint. I try not to surprise students. It's in there. Stuff is in there. What you need to know, what you need to get to test it on. But anyway. Right. But this is from basically the textbook that I'm writing. So it goes back a little bit of what we mean by statistics. And again, I'll give you just 2 minutes on this. First of all, when you mention the word statistics, if you're from, say, American upbringing, you generally think of sports statistics. Okay? So American kids are different from Thai kids. In fact, you often hear things like, you know, over there, they don't teach you to memorize. Well, the reason they don't teach you to memorize is not because memorization is not important. It's because memorization is so important, it's already ingrained into their culture. That's why they don't teach it. Okay? When I went there when I was 14 years old, it's amazing. At that age, we would, you know, if you want to brag, you brag about what your dad does for a living, what car you drive, and so forth. You know what American kids brag when 14 years old brag? They brag about how well they memorize baseball stats. They know exactly who in which season has certain batting average. Okay? So it's not that memorization is not important in education. It is important, but it's not yet ingrained into our culture. So it has to be taught. Okay? Whereas in other culture, memorization, look at history program. You know, if you look at history program from the West, you have recording of history that's not done by somebody official, not by somebody from the royal palace, but a farmer would write records. Okay? An ironsmith would write records. that becomes a description of the plague or something like that. So in the West, they have a very deep love of memorization already. Okay, so when you go to hear silly people talk about, problem with Thai education is that they want you to memorize too many things. That's stupid. That's like you take a 2 weeks orientation at American school, and you say, oh, they're not teaching you, they're not requiring you to memorize anything because it's already ingrained. Okay, you have to understand where it's coming from. Anyway, that's I digress. The difference is sports statistics is your achievement against your peer. So from our perspective, sports statistics per se is not data, because the conclusion you have is about individual and how he stands out or does not stand out against the peer. It's like performance statistics. It's like saying that an average return on investment, if you invest in a mutual fund, is 3%, or maybe 1.2% risk adjusted. But this trader that I just hired is very good because on a risk adjusted basis, he's getting 2%. So he beats the market. It's that kind of statistic. It's kind of individual. Well, that's not what we're about. We're about learning the population. Okay? We're not trying to glorify, make Rooney an individual sports person against a peer. Okay? So, how about statistics on floods and famines and pandemics? Again, this you're not that familiar because you live in a very comfortable countries. Your life is never threatened. But if you live in Europe, your life is perpetually threatened. Okay? So they keep good records on floods, things like floods and plagues and things like this. So they're very interested in statistics because their lives depend on it. Whereas people in a gentler climate like ours, we tend not to care so much about statistics because our lives are always good. Okay? Whereas you go up the latitude, lives are much harder. And based on certain years, you literally will be starving to death or risk starving to death. So a lot of calculation, a lot of year-to-year statistics is important. Finally, population statistics, and that's really where we come in. Okay, we come in from trying to analyze probably statistics about population to infer about population. Okay, and that's what learning. Now, what do we mean by statistical measure? Now, these are the 4 things that I mentioned. Okay, so that's a repeat. Okay, what do you mean by chart? Actually, charts, I just want you to focus on 2 things. One is the histogram, and one is the scatter plot. Okay, so histogram, for example, I'll show you. Now, this is kind of 2-dimensional histogram. This is basically, I downloaded the example data from the Wolfram mathematical site. This is the Old Faithful. You know about Old Faithful? It's a geyser. Geyser is a hot, steaming jet of subterranean water. All right, very hot, very hot. And the thing is, you can actually keep statistics on how long you have to wait for the next one. And once you wait, how long does it last? It turns out it's a bimodal distribution. On this axis, this is like 5 minutes, I think. Yeah. So this is minutes, 2 minutes, 3, 4, 5, and that's 80 minutes of wait time. So the longer you wait, the longer it lasts. Okay. So that's natural, right? Water builds up pressure. It takes a long time. It builds up. It takes a long time to build up the pressure. Once it builds up the pressure, there's a lot of volume there to release. So the longer you wait, the longer the geyser shoots. But what's interesting is that there's actually 2 modes to this. Okay, 2 modes, but this is a different way of plotting. Okay, so you can look at this one. This one is like you smoothen kernel. So you can see there's like a short wait, short burst, and long wait, long burst, but nothing in between. Okay. Now this is sort of thing that scientists spot, and they say, there's a pattern. And this, the reason I want to mention this in particular, even though I'm just using this to illustrate histogram, is that as a data scientist, literally that's what instinct you should have. Okay? You shouldn't just be very good in programming, Python or mathematical or whatnot. You should have a scientific instinct. Say, there's something there. Okay? Now, your interest may be different. Your there must be something there. Could be something about consumer pattern or internet clicks and so forth, and that's your thing, right? It could be about, so it could be about e-commerce. It could be about all kinds of social network events. But the instinct to say, there is something. Okay, this doesn't happen just willy-nilly. Okay, that's the reason why there's a two very well-defined peak. And this, of course, is called multimodal. Now, when I said mode, that it means it's the most frequent, right? So technically, there's only one mode because there's only one combination that's most frequent. But in this case, it's actually called two mode because when you say modal, you mean relative. So it's like a hilltop. Okay? It's not the tallest hill ever, but you can certainly distinguish this from having just one hill. This is two hills. Right? So this is bimodal distribution. Okay? The by two comes from the fact that there are two hills, not from the fact that it's two dimension. Okay? You can have two dimension, no hills. You have one dimension, many hills. Okay? So that's your histogram. And in fact, I pointed you to a Wolfram website and a video, and the video also uses this data. In fact, it's the video that points me to say, oh, this data is interesting as an example. So I point that. In fact, I kind of copy their method of display. I thought it's very nice, so I repeat it here. And the scatter plot, of course, you're familiar with it. For some reason, I don't have the answer. I don't have the example. Now, I'll come back to this. Okay, talk about that already. Intuitive, combinatoric, frequentist. You have this in your note. Okay, now the meat. You need to have something called random variable. That's the most critical thing. If you don't walk out of here understanding random variable, then I fail. Okay? Well, let's take it at face value. It's some kind of variable. So it's x. It's x, right? Variable means it takes on different value depending on whatever. Okay? Now, if x is the height, and I randomly pick you, and I say, how tall are you? That big X, okay, this is where I like to use the blackboard. Never mind, it doesn't have to be recorded, it's very minor. So the big X is some event. Event is measure the height. It's equal to little x, that's the actual value. Let's say you are 165 centimeter. Okay, so that's x height of somebody. X is a random variable. You don't know what the value it is. Okay, it takes on different value. I randomly pick you, so it becomes 165. So it's called random variable. Now, if you actually know what you're talking about, if you know the mathematical foundation, it's not random. It's not a variable. Okay? You know why it's not random? Because if I pick you and you say, I'm 165, and I pick you again, can you say something else? No, it's not random. You're always 165. It's also not variable because it's a function. It's a function that assigns this person, a human, an animal, a desk, a table, I don't care, to a value. It's an assignment, it's a function. Okay? What is random is the process of getting to that. Okay? Anyway, but it's very profound mathematics that this thing captures, but we'll skip that. It's a lot of fun, by the way. Okay? So that's what random variable means in your language. It's a variable that's random because you don't know what value it's going to take. It takes some random value. Okay? You can answer that in the exam, and I won't penalize you for that because 90%, 95% of the population will understand random variable that way. Okay? Now, What is probability distribution? It's giving probability to that. There's a probability of x being 160. If I do this, probability big X equal to little x, okay? And I do it for all the little x. Then it becomes a function. That function I call little p of little x. Okay. Let's just say that out of 100 of you, 10 of you are 165 centimeters tall. So what is probability big X equals to 165? In other words, what's the value of the function p of 165? That's 110. Right? 10%. If there are 25 of you who's 175, then I'll say p of 175 equal to 0.25, and so on. The point is, once I run through all the combination, they all have to add up to 1. That's what we agree. Okay? And if there are no freakishly tall, there's no 2 meters tall, then 0. Correct? So this becomes what? So you can say 160, 161, 162, 160. Then I can put a bar chart, right? What does this look like? Well, it looks like a histogram, doesn't it? Right? Except a histogram would give you the actual number. Whereas this one just divide by 100. So what? What's the big deal? You can have percentage histogram, right? So first of all, think of histogram. Think of percentage histogram. So once you become histogram, all the height add up to 1, right? Something that's not possible is 0, and you can only have 1 height. So this probability mass function, it gives you the probability to the value. It is a function. The reason it's called a mass is because it's concentrated like a mass, like a ball. This probability is clunked. It's literally assigned to this mass, this value of 165. Not 165.5. It gives you 165 because that's how you measure. So it's actually to a point mass, right? So mass in this sense means like a point. Probability mass function. Correct? That's it. So what's the difference between PMF and probability mass function and histogram? Well, a PMF is only a true PMF if I'm never going to see another human being again. You know, you are the human being. That's it. There are only 200 people left on Earth. The rest are eaten by zombies or something. So that's the population. So you can imagine the PMF is the histogram of the entire population. Okay? But in reality, the world is still okay, right? There are people out there. So if I say I make a histogram of you, then it's just a histogram of 100 people in this room. It's not histogram of population. So you can imagine that PMF is quote unquote. Now, don't put this down on an exam. It's silly. It's the hypothetical histogram of the entire population. Okay. There's another reason why I don't want you to stick to this analogy too strongly, because the notion of population is not finite. When I say population of people, I can say, yeah, it's finite. You know, 7, 8, 9 billion people. Okay, that's finite. It's a lot, but it's finite. But actually, that's not finite. What if I talk about human beings who are yet to be born, right? Or a population of events, population of stock prices, tomorrow, the day after. Okay, so you can't really have finite population. So this idea that you hypothetically have the histogram of, you know, that would be like if you can see the future and all that, then you can say that. Okay, so you can say PMF is a hypothetical histogram of all the population till the end of time, something like that. Okay, which you can't really. Fine. Now I want to make some shirts. and I want to sell them to students. And I want to know that if I make this size of shirt, you can wear shirts that are too long, right? You can't make it too short. Okay, you can make too long, make too short, let's say. So what's the probability of X is less than or equal to 175? If I knew this, and this gives you something like 80%, I'll just pick some number that covers 80%, and I'll make the shirt of that size, and I can sell 4/5 of the people, no problem, right? Right? You don't want to make it too large, you don't want it too small, but you want to cover a good percentage. This is cumulative. Now, the word is cumulative distribution function. Okay, CDF. Can you see that? Nope, you can't see that. Okay, so for some reason I didn't write that down. So it's CDF. It's PMF and CDF. You got that? Okay. Now, so far, I talk about your height in centimeters. Okay, I talk about your height in centimeters. What if I want to talk about your height in a little bit more details? Because I'm not just making your shirt. I'm making a medical diagnostic. So I want it to be continuous number. Now, technically, there's no infinite precision. Okay, when somebody takes your blood count, your blood value, some glucose level, you don't have infinite precision. Same with your height, but you have continuous value. In other words, you're not just 165. You 165.17282934581, right? So if you think about it, if you make the histogram fine enough precision, instead of having just 10 blocks, you have 20 blocks. If you have hundreds of blocks, the histogram, you can count the number, you can put in as parameter, right? Literally, you know what the histogram is going to look like? It's never going to look like this. This is what you think. It's going to be a histogram of people's height, right? If you make it small enough, it's going to have the same height. Just small over here. Why? Because no two of you have the same height. In fact, I don't know what that value is. So if it's continuous value, X equal X is meaningless. You don't have exact equal. So with continuous value, the fundamental quantity you talk about is not this, but it's this. So with discrete value that you can count on your hand, right? Okay, it's called countable set. Technically, it's called countable. Oops, I just opened the wrong one. Okay. With discrete random variable, okay, random variable takes on countable set. Okay, by the way, countable is a tricky sense. It's countable not by man, but countable by spirit or something, by God or whatever. Okay, meaning you can count. It's like number is number of seconds. You can count 1 second, 2 seconds. You can't stop. Countable means you can count, but you can't stop. Okay. If you can stop, it's also countable, but it's finite. It's even smaller than that. Okay. So from a countable, it's probability mass function. If you have less than equal sign, it's cumulative distribution function. But for what? But for continuous, you can't start with equal sign. You have to start with less than equal to. And in this case, okay, so you have P little x equal to probability big X equal to little x. Okay, that's PMF. Big P of X is the probability of X less than equal to little x. That's called CDF. Okay, now traditionally, by convention, when you start with continuous random variable, you're talking about the same thing, X equal to little x, but you don't use P, you use big F. Okay, use big F. Now, you would like to think, if you have small p adds up to big P. And you have big F. You have to wonder, is there a little f? Yeah, the little f would be something like this. But you can't do that, right? You can't do that. So in fact, what you can do is, if little p becomes big P by adding, and adding in mathematical speak is integration. Yeah, little p integrates, becomes a big P. How does big P becomes little p? Differentiate becomes little p. Same story here, but you start with big F. How do you get to little f? You differentiate. Right? Now, let's look at picture time. Picture time, this one looks like histogram, right? This one looks like cumulative histogram. Well, this one also looks like cumulative histogram, but it will be continuous. So it looks something like that. What's the derivative of that? It's going to look something like this. It grows slowly, grows quickly, grows slowly. Small, high density, low density. So it's the density of probability. Therefore, this one is all CDF, but this one is called P, not mass, not concentrated at a point, but around values. So it's a density function. Okay. Now, those are the two things that you can't walk away without. First is the concept of random variable. Don't have to take picture here, guys. You have internet at home. Okay. PMF, PDF, CDF. Okay. Not computable document format, but CDF, cumulative distribution function. That's it. That's it. You're gonna see a whole bunch of this. Now, let's do a little mental exercise, just for fun. If this is your big F, this is your little f. If this is your little f, what's your big F look like? Well, it's gonna grow sharply here and not so much sharply there. See? Let's do the opposite exercise. If this is your big F, what's your little f? Huh? Because this is the slope, right? The slope is flat, so that's 0. That drops down to 0. The slope is flat, that goes down to 0. Okay? There's a tiny slope here, so there's a increase there. In fact, it does get long enough. Okay, so that's that. So now I'm going to talk about expectation. Maybe I'll come back to it. But if you think about it, if you build a whole bunch of little f, little big F, little p, big P, and you take that into your bags, right? And you take some sample from the data, can you match the picture? Yeah? Imagine, yeah, when you were kids, when you were about this big, you had to play this game, right? Triangles with triangles, or yeah, it's the same thing. You're just playing the matching game. Except instead of matching this, exactly that, you match the general shape first. Then you get the parameters to match exactly. Right? That's the name of the game. So let's look at some example. So I just created okay. You have this as CDF. Basically, these two are equivalent command. Okay. I just want to give you a little bit of heads up. The name one of the recipe, yeah, let's call them recipe, different models of different recipe. One of the recipe is called binomial distribution. Okay, and that recipe has two ingredients called N and P. And how you specify N and P, you get different variation. Okay, it's like different flavors, but still same dish. If I say if X, okay, this is how clever Mathematica does. Literally, you can do two things. This is called function. You specify this thing called binomial distribution function. You create an object. You say, I'm talking about binomial distribution function. It has N equal to 7, P equal to 0.5. Never mind what that is. That's my sauce, right? I put in 7 cups of sugar and 0.5 liters of lime juice or something like that. And that's my dish. I want the PDF of this. Now, having said this, because in Mathematica, it's all the same function. Whether you talk about CDF here or CDF here, big P or big F. And also to an extent, little p and little f is the same. So in Mathematica, this will be called big C, big D, big F. And this one will both be called big P, big D, big F, PDF. So there's no PMF in Mathematica, okay? And in fact, the reason you have big P, big F, little f is sort of like historical. Okay, it's how I've been taught. It's how it's in the textbook. You look funny if you use different notation. But so what I did was to say I'm talking about this recipe for distribution with this parameter and the PDF. PDF is probability. In this case, it's probability mass function. Okay, of X from 0 to 7. So that gives you this number. Okay, this gives you this number. In fact, this command gives you this number. Alternatively, if you want to be more elegant, you can say, give me table of probability of X equal to X. See, that's PMF right there. Assuming that big X has a binomial distribution with 7.5. So it's equivalent command. One is from a probability viewpoint, if you use that. One is from a functional viewpoint, if you are more of a programmer. Okay, it's the same thing. Can do both. But this is what it looks like. 0, P of 0, P of 1, P of 2, P of 3, 4, 5, 6, 7. Anybody want to guess what binomial distribution is? Well, binomial, from bi, no, meal. No meal means term. No meal, no, name. Bi means two, right? Two term. So it's either boy or girl, yes or no, head or tail. If I toss a coin and it's head, I call 1. If I toss a coin, it's tail, I call 0. Okay? So this is binomial. Okay? If I have one coin, it's called special coin. It's called special binomial, called Bernoulli. Now, Bernoulli doesn't break into terms. Bernoulli is the name of the family, name of the guy who invented. Okay? So a coin toss is what? Again, I'm mapping the face of the coin to the number. But I'm mapping head to 1, 0 to a tail to 0, right? If the coin normally is fair, the probability is 1/2. Well, Bernoulli just means it's a coin toss, but the coin does not have to be fair. It can be 0.7 and 0.3, right? So it's like roulette wheel, but instead of having half, you have 70% and 30%, right? So what's the difference between a coin toss and picking one of you at random and asking, are you wearing glasses? Right? The difference is most of the time the coin is 0.5, right? The glass is 0.3. Okay, well, that's called Bernoulli. Okay, and this is how you write. And maybe I should use this just to make it formal. Next week, I hope to be able to write on the iPad because they're getting a pen. Or if you guys have extra pen, you want to donate, or let me borrow. But okay, so let me do the summary. So if I write this, big X is Bernoulli. Okay, and I put a little p. Okay, that means p, little p of 0 equal to probability X equal to 0 is equal to 1 minus p. P of 1 is here to probability X equal to 1 is equal to p. 1 in this case is the positive case. Now this is so trivial, but it's the most fundamental because 90%, well not 90%, 70% of your data science job will be involved with binary discrimination. Somebody gonna buy, somebody not gonna buy. Yeah. Is your client going to leave your account or gonna stay? Yeah, the world is complex, but chances are you can aggregate into two paths. Yes, no. So the binary is so critical to your, it's not just binary because computer is binary, but because literally the way you deal with things in life usually is binary. Okay? People are not perfectly good, perfectly bad, right? But you can say, hey, he's a good guy, he's a bad guy. In the sense that, yeah, you can hang out with this guy, you don't want to hang out with this guy. It's binary. Okay? Even though once you have decided to hang out with this guy, he has a lot of flaw or something like that. Or bad guys also has good point. But yes or no, I'm going to hang out with this guy. I'm not. This client going to buy something, not going to buy something. Well, that's called Bernoulli. Now, let me erase that. Erase later. Trash later. Clear all drawing. And I say X is binomial. Now, it's spelled B-I-N, not binomial, because that's tradition. It has parameter P, but it also has parameter N. Okay? If this is the case, right? Whereas X is equal to sum I going from 1 to n of xi. Where xi is independent, identically distributed, Bernoulli. That looks complicated. It's not. It's just saying you're tossing the coin independently 8 times and you count the number of heads. Right? Independently, has to be independently. Okay? So, if the event, the random variable is eyeglass wearer. What's that what's that random variable? It's Bernoulli with probability p equal to 0.3, right? Because I pick randomly and boom. If I do this 10 times, around 3 times I get glass wearer. But if I don't pick once, I pick randomly 3 times. Now, when I pick randomly, if I pick you wearing glass, or doesn't matter if you wear or not. Once I pick you, I'm not going to pick you anymore. And I'll pick the other. Is that independent? Not independent. Because once I pick you, if you're wearing glasses, I take you out of the pool. the remaining probability of wearing glass is less. If I pick you, you're not wearing glass, and I take you out of the pool, the probability of not wearing glass is lessened. So it's called sampling without replacement. Now, to be independent, you have to have sampling with replacement. I pick you, then I throw you back and pick again. Now, I may pick exactly the same person, or I may not. Doesn't matter. Doesn't matter. Okay. The point is, the reason I threw you back is because I want the probability to be the same as before and independent, right? It has to be independent. Yeah. So sum of IID, the first I is independent. Second I is identically distributed, means has the same distribution. Because you can imagine that independent in this sense, I pick a glassware from this class, and I go pick a glassware from another class, but another class has probability 0.2. It's not identical. It's independent, but it's not identical, right? I want independent, identical. So either I pick you and I throw you back and I sample again, or I can go to another room, but that room has to have the same percentage, right? Has to have the same identical. And so basically, that's that. Now, let's go back to our little, why does it have to be identical? Well, it doesn't have to be identical, but if it's not identical, you don't get this. It's a restriction. But as with all things, in mathematics, if you are willing to make some restriction on the applicability, you can make a lot more conclusion, right? In other words, if I knew that the basic event is Bernoulli, and I knew that I'm taking the sum of independent, identically distributed, I can do all kinds of analysis, which we're talking about. If it's not, the game's over. Well, it's not over. You can do more things, but certainly you cannot do a lot more. Once again, this is always a trade-off. If you're willing to make the restriction on the problem that you deal with, you can do a lot more analysis. Now, in reality, this is what happened. The assumption, this is called assumption. IID, this is an assumption. It's not perfectly guaranteed, but you're willing to say, close enough. For example, I pick you wearing glasses, and I throw you back, right? But because you were picked once, you're really shy, you run to the back of the room, okay? So really, there are 30% of glass wearer, but the chance of me picking another glass wearer is a little bit smaller, right? Because I already picked her and she ran to the back of the room and said, I'm so scared, right? So the assumption is not perfect, but you're willing to say, close enough, okay? That's like relaxing the assumption or something. Now, technically in mathematics, if you relax the assumption, you literally assume the assumption is not met. But in this case, I'm talking about quote unquote relaxing, like, yeah, will do, good enough.
So the sampling without
it has to be with replacement. Without is something else.
when you pick me and I'm wearing the glass and you take
I just write down and say 1, and I throw you back.
back in the room.
Back in the room. Okay, and assuming you don't get scared and run away, you just do it in the same mix. And I randomly pick again. I may pick you again. I may pick somebody else, right? I still have the same probability 0.3. Okay, so if I pick 3 times, then the number is not between 0 and 1 anymore, right? It's between 0, 1, 2, 3, 4. Oh, sorry, 3. Okay, and each one has the probability of different. What's the different probability? Okay, let's go. Break on it,ครับ. Okay, guys, bowel movement time, 5 minutes.